Hello, we are the Satickens, and welcome to our design review presentation. I'm Henry Lee.
And
Logan Weinstein.
Jaden Sa.
Akash Nathan.
Our project statement is that we understand that the collection of plastic waste in the Earth's ocean is an ongoing challenge for the global community. To monitor the collection of plastics in order to remove them, the Satickens have developed a satellite solution. Our solution is to develop and assemble CubeSat subsystems which can power and support an optical payload, while at the same time, the CubeSat analyzes the data of detected colored plastics on the surface of the ocean, rivers, and lakes, and wirelessly transmits the data to the ground station from low Earth orbit in space.
so these are the requirements for our CubeSat operation. The CubeSat shall communicate with the ground station using the UHF amateur band. The CubeSat shall take one image every 2 minutes when it's over the ocean and in sunlight, and shall save the image. The CubeSat shall operate primarily on solar panels while using a lithium-ion battery as a secondary source when the sunlight is not available, and the CubeSat will operate in the LEO orbit.
For our systems block diagram, we separate our system into 6 subsystems, and each of the components in this subsystem is connected together either through power, which is represented through the orange arrow, data, which is represented through the purple arrow, mechanically mounted, which is represented through the red arrow, or like a combination of 2 or 3. For example, if you were to look at like solar panels, you can see that it is physically mounted to the structure, but it also sends power to our battery, which would send power to our Raspberry Pi. Yeah,
So for our mechanical layout, we designed a prototype of the CubeSat in Autodesk. And for this design, we have acrylic plexiglass panels that surround the structure and that allow you to see transparently into it, which gives you like a view of the electronic components, such as like the Raspberry Pi and the IMU, which are connected through jumper cables. Also, there's these L brackets on the model, which kind of mount the structure and keep it in one piece. Also, there's an electrical wiring diagram that we included on our multi-view drawing that shows the connection between the Raspberry Pi ports to the sockets on the IMU. And lastly, we have a battery on our model, which gives power to the Raspberry Pi and also allows the camera on the bottom of the model to take the picture of the plastics in the ocean. So for our mass budget and bill of materials, we have a list of the parts that have certain properties on them. And down at the bottom, we totaled up the quantity, mass, and estimated cost, in which there's 56 total components. It has a total mass of 0.25 kilograms and a total cost of $176.51. And the parts are showed through the isometric view with balloons that show the specific parts on the model. And also, the model is comprised of subsystems such as the battery, the IMU, and the Raspberry Pi, which are connected through those jumper cables, and the camera, which takes the picture. Lastly, there are marginal room in the model, such as the potential cost savings and also the mass savings. So for the cost savings, the jumper wires can cut the cost down by purchasing them individually instead of as a group. And also the acrylic panels can be utilized by cutting them specifically so that no parts are wasted. And the supplies can be saved by using a workshop instead of purchasing the supplies individually. Also, the potential mass can be saved by changing the material, such as the aluminum rails, to a lighter metal that cuts the mass down, and also changing the screws to a lighter version so that the mass is reduced.
Okay, so for our software architecture, for each of these components, I color coded them to show what they do. So pretty much green components are systems that send data or get data. That's to be more accurate. And the blue boxes on top are conditions that tell the system when it should take a picture and like when it shouldn't. And then the gray component tells it whether it should even send the picture or not, or whether it should just delete the picture because it's useless. And then the yellow represents the Earth, so it sends all of the pictures to our ground station, which is GitHub pretty much, and that stores all of our data.
We calculated the link budget for a LEO CubeSat using the UHF amateur band. And the CubeSat has a 800 kilometer circular orbit, and it's assumed that it's directly above the ground station. So the uplink calculations are the equivalent isotropic radiated power was 22 dBW. The free space path loss was 83.31 dB. Received power was negative 61.31 dBW. The noise power was negative 144.26 dBW, and the SNR was 82.95 dB. And the downlink calculations were for equivalent isotropic radiated power, it was 0 dBW. Free space path loss was 83.31 dB. Received power was negative 71.31 dBW. The noise power was negative 146.53 dBW, and the SNR was 75.22 dB.
The data budget. For the data budget, we first needed to discover the average image file size and downlink rate. So we took 5 images, and we found the kilobyte size of them and the time it took for them to downlink. And we discovered for the average image, it was 512 kilobytes with a downlink rate of 0.46 seconds. We set the picture time to 5 seconds, and the height was 720 pixels with a width of 1280 pixels for all of the images. We know that the pictures have to be taken over water in the daytime, and the picture has to be taken at 2-minute intervals. Given that the demo duration is 90 minutes and the percentage of the Earth's surface that is water is 71%, with a sunlight percentage of the mission of 50%, we know that the image taking duration is 31.95 minutes. Given that each picture will be taken at 2-minute intervals and each picture takes 5 seconds to take, we know that the Raspberry Pi will be in the camera state for 75 seconds. Given that one image is 512,000 bytes with a downlink time of 0.46 seconds and the demo duration is 31.95 minutes. We know that a time to downlink all of that data would be 6.9 seconds with a maximum of 15 images that can be sent, with a total data that is being downlinked of 7,680,000 bytes. For the power budget, we split up the power usage into the different states of the CubeSat. There's the picture and save state where we take a picture and then save it to the Raspberry Pi, where we use the Raspberry Pi, the IMU, and the camera. The standby state where the Raspberry Pi is still in orbit and doing no other actions. The downlink state where the Raspberry Pi is sending down information to the ground station. For the picture and save state, we know that the Raspberry Pi takes less than 5 watts, and this power is also redirected to the IMU to power it as well. And the camera takes 0.9 watts. So we know the total power usage is about 5.9 watts. And because we're in that state for 75 seconds as previously calculated in the previous slide, we know that the power in the picture and safe state is 442.5 watts. In the standby state, which is the state we're in the longest, only the Raspberry Pi is running and it's only at an idle state. And so 2.7 watts are used per second. And because we're in that state for 5,316 seconds, we know that the total power usage in that state is 14,353.2 watts. And finally, in the downlink state, where the Raspberry Pi is also only the Raspberry Pi is running, but at a increased power usage because it has to downlink the data at 5 watts, and it's in that state for 6.9 seconds as previously calculated. We know that the power usage is 34.5 watts. And we can sum those up in the table on the right, which describes the power usage of all those states together. The power that we need to accommodate all of the power usage comes from the solar panel. And for this mission, we were provided the Dreamlight 2-volt solar panel, which only gives 0.12 watts of power usage per second. And given that we're only in this state for 2,700 seconds, we can only produce 324 for the whole duration, because 2,700 seconds is half the duration of the mission, because we're only under sunlight for half the time. We understand that it's inefficient to power the mission as a whole. So we discovered that to power the mission as a whole, we need a solar panel that can produce at least 5.45 watts of power per second. And to accommodate this, we use an example as shown with the SoShine 5-volt solar panel, which can provide 6 watts of power. This example showcases a way that we can provide the power we need to complete the mission. With this, we understand that the battery takes 20 minutes of charging time to charge to 100%, and the discharging time, which is used by using the power usage of all of these different states on average, and we use that to discover that 2.2 hours is the discharging time for the battery. Given all that information, we discovered that with the SoShine 5-volt solar panel, which is an example of 6-volt solar panel, we get 16,200 watts, and this accommodates for all of the power that we previously used on the previous slide, and we get a net positive sum of 1,470 watts.
All right, for our integration test plan, the yellow coded boxes are for integration and the green coded boxes are for testing. So you first begin with integrating the structure, then to our communication, and then the ADCS, and then the power. And we would go on to test the imaging and test the software and integrate the propulsion and test it. And we will integrate the thermal system and the solar panel. And we'll test the communication, test the caustic and vibe, test the thermal, and integrate the system confidence, and integrate the made to launch vehicle. And finally, we can test the launch-based confidence test. For a concept of operations, our CubeSat will be orbiting in polar orbit and LEO orbit with the altitude of 800 kilometers. The CubeSat will be launched from William Howard Taft Charter High School. It will be deployed, and the CubeSat will receive commands from our ground station. Then it will calibrate for 2 minutes and take an image, and it will repeat 15 times. And from then, it will be in standby state because we need to conserve energy in order to carry out our entire mission. And until it downlinks the collected data back to the ground station, and it will complete our mission. Okay, thank you, and we hope to see you in the final event presentation.